Okay, so let me first thank the organizer for giving me the opportunity to give a talk at this historical conference. My first serious thought about QCD probably happened in 1998 when it was a time of color superconductivity. So basically, I've missed the first half of 50 years of QCD, and it's an honor for me to be here speaking in front of people who have been at the beginning of QCD. I'm going to tell you about, oh, by the way, before starting, let me mention that for the last more than 10 years, I've been thinking about quantum matter, condensed matter physics a lot, and I've seen a large cultural impact of QCD in other fields, including theoretical condensed matter physics. QCD is not only the first theory, a complete theory that is valid from the deep IR to the UV without the need for the cutoff. It's also probably the first example of a theory in 3+1 dimensions at least, where the microscopic degrees of freedom is different from the low energy degrees of freedom. The quark and gluons that we put in the Lagrangians are not the asymptotic state at low energies. And that has an immense impact on condensed matter physics. Around 1984, 1983, people started to realize that in the fractional quantum Hall effect, we have a similar situation in which the microscopic theory are the theory of electrons, but the quasi-particles in the fractional quantum Hall state can be fractionally charged, like the Laughlin quasi-particle in filling factor 1/3, or a composite fermion, which is a fermion similar to electron but is electrically neutral. Also, if you read the condensed matter theoretical literature now, you would see very familiar terms like deconfinement, partons, used in a slightly different context than QCD, but the fundamental idea is basically the same. So in this talk, I'm going to tell you about something that in this conference has been called the chemistry of QCD, basically the physics of nuclei instead of quarks and gluons. Still, it's not QCD, but it's still the physics of the strong interactions. But I'm going to tell you about probably an exotic, maybe a simplest chemistry possible in the real chemistry. That would be a chemistry of the helium-2 molecules. Heliums form a molecules, helium-2 with a binding energy about 10 to -7 electron volts. Here we are going to talk about nuclear physics at a very small energy scale, about 0.1 MeV to about a few MeV. And our the non-trivial physics in this range of energy comes from the accidentally large fine-tuning in the interaction between two neutrons. The neutron-neutrons scattering length is about -19 Fermi, which is much larger than the range of the interaction between neutrons. And as we will see, it has this fact has a non-trivial effect on the rate of reaction with several neutrons in the final state. So let's consider, we are going to return to this reaction a little bit later, but as an example, consider the absorption by triton nucleus, a pi minus. So let's assume we have this reaction, and one can have a situation in which we produce a gamma particle and 3 neutrons. The energy range for the photons is from 0 to about 130 MeV. So that's because the mass of the pion is 140, but we have to break the tritons. So the spectrum of the gamma is continuous, and the differential cross-section, let's assume that we detect only the photons, but ignore the neutrons. The spectrum the differential cross-section will have this form, and we are interested in the behavior of the differential cross-section near the endpoint, where the energy is very close to the maximal energy of possible. We will show that near this endpoint, the differential cross-section behaves like E0 minus E to the power of 1.77. And that number, 1.77, is related to the dimension, the scaling dimension of an operator in something that we will be calling non-relativistic conformal field theory. So let's see, how do I go further?
Touch the screen. Touch the screen.
Yeah, I touched this laptop, but still it's. Okay. Okay, thank you. So it's a jump a lot, but let's go back. Somehow I'm going in the wrong direction, maybe. Not sure where I'm going. But we are going somewhere. There's your...
The lower button.
Lower button. Oh, I see. Thank you. Yeah, the upper button. Yeah, take me very far. Okay. The plan of my talk is the following. First, I'm going to tell you about non-relativistic conformal symmetry, so-called Schrödinger symmetry, and then describe non-relativistic conformal field theory. One of the examples that we will be considering here is fermions at unitarity. And then we are going to talk about neutrons and what we call unnuclear physics. And the references that on the basis of this talk is given is the paper that I wrote with Yusuke Nishida in 2007, paper with Hans Hammer that we wrote in 2021, and an upcoming paper with Chowdhury and Mishra, a postdoc, and a graduate student at U Chicago that I hope will appear very soon. Okay, non-relativistic conformal symmetry. If we can go there, then we will learn that. Yeah, let me see. Okay. Yeah. Oh, I have to click on these here.
Yeah,
Or,
you just went too far. So try it now.
yeah. Okay, so let's consider a simple free space Schrödinger equation written here. We ask the question, if we have one solution, can we generate other solutions? One way to generate a new solution is to multiply this old solution by a phase. And that's related to a conservation law. It's conservation of particle number or conservation of mass. And then we have translation in space, translation in time, and rotation. These can also be used to generate new solutions. We have Galilean boost, which looks slightly more non-trivial than this phase rotation. First, we have to shift the coordinates x by x minus vt, keeping t invariant. And then we have to multiply the wave function by a phase factor, which can be found by just trial and error. Try to find the phase factor to satisfy so that the new field satisfies the Schrödinger equations. And then there is dilatation, in which we change the coordinate x by a factor lambda and coordinate t by a factor lambda square. And one can see from this equation that the new field will satisfy the Schrödinger equation. There is, however, one transformation that you usually don't see in textbooks, and that is this one. You do t goes to t over 1 plus alpha t, and then x to x over 1 plus alpha t. And the quickest way to see that this is a solution is probably the most boring way. You just put this into the equation and check that this equation is satisfied. It's called, I would call that a proper conformal transformation in analogy with the proper conformal transformation in the relativistic theory. Our theory has scale invariance, but in addition, there is this invariance, the free Schrodinger equation. And we can play with the algebra. All these transformations generate infinitesimal changes of the wave function, and we can do two transformations in one way, and then going back in the reverse direction and compute the commutator of these generators. So here's the table. One thing that one has to see is that the number of particles, that is the phase rotation of the wave function, commuted everything. So we have the algebra, which is now called the Schrodinger algebra, in which the particle number is the center. One can build up a formalism of non-relativistic conformal field theory in analogy with relativistic conformal field theories. Introduce notion of local operators. Each of a local operator would be characterized by its particle number of mass. So if you commute that with the operator of particle number of mass, that I assume the particle and mass can be used interchangeably because all that I have is one type of particle. And then one can also talk about the dimension of the operator. So for example, the operator psi would have particle number 1 in dimension 3/2. And by dimension here, we have to be careful. The dimension of momentum is 1, dimension of energy is 2, because omega is equal p squared in non-relativistic theory. One can also define so-called primary operators. So for these primary operators, the correlation function are more restricted by the invariance. For example, the 2-point function of a primary operator would have this form, where the form is completely fixed, only the numerical coefficient in front is arbitrary. The example of non-relativistic conformal theories are the following. So first, a theory of free non-relativistic particles is Schrodinger invariant, non-relativistically conformally invariant. In 2 spatial dimensions, one can show that anyons, that are particles with fractional statistics, can be also conformally invariant. But the example that is most relevant for nature is the example of spin 1/2 fermions at unitarity. These fermions, this theory is realized in cold atom experiments, but it's also approximately realized by neutrons, because the neutrons have large scattering length. So let me see. Yeah.
While you're working, tell me what at unitarity means.
So here unitarity is it's somewhat of a legacy terminology. When we take 2 particles, 2 neutrons, then consider the elastic scattering at very low energy. Its cross-section almost saturates the unitarity bound. The S-wave scattering cross-section saturates the unitarity bound. It's a bit confusing terminology, but it's quite established in condensed matter, in cold atom physics. So, but let's consider this system in a more mathematical language. We know that in non-relativistic physics, the Fock space is very simple. We have some number of particles, then this number of particles is not going to change. There is no particle hole creation. And so we can talk about the wave functions of a system of m spin up and n spin down fermion. And this number m and n is going to be fixed. The wave function has to be antisymmetric when we exchange 2x or exchange 2y. And here, in this theory, when you have one spin up and one spin down particle approaching each other, the boundary condition for the wave function for this unitarity fermion is non-trivial. The wave function diverges as 1 over the distance x minus y And then if we expand this wave function in series over xi minus y, only the odd powers appears. So now that this set of wave functions combined with the Hamiltonian, which is defined to be just the sum of the kinetic energies, is a consistent quantum mechanics in the following sense, that with the active Hamiltonian on a wave function, it doesn't take us away from that space of wave function, and also the Hamiltonian is several joint, is Hermitian. Now let me define the notion of local operators. One of the simplest operator in quantum mechanics, in the second quantized version of quantum mechanics, is the annihilation operator, and it's defined in the following way. If we have a one particle state with a wave function psi, then the matrix elements of this operator between this wave function and the vacuum is equal to the wave functions. Very simple. So let's call that a charge 1 operator. Charge here means the particle number. The dimension of this operator is 3/2. Now consider a charge 2 operator. In quantum mechanics, we can take two operators, psi down and psi up, that annihilates a particle with spin up and spin down at two different points, x and y. Such an operator, when acting on the two-particle state with the wave function psi, give us the vacuum with the amplitude equal to the wave function psi as a function of x and y. Now, I would like to have a local operator, that is an operator defined at one point. And usually in quantum mechanics, I can just take the limit y goes to x. But here in the quantum mechanics of unitarity fermions, that operator doesn't exist, because the wave functions psi x and y, when taking y goes to x, goes to infinity. The boundary condition we put in is that the wave function diverges as 1 over x minus y. But one can define another operator with prescription very similar to the point splitting in quantum field theory. We take psi x times y and then multiply to x minus y. This operator now would have a finite matrix elements between any two-body state and the vacuum. And this is now a well-defined local charge 2 operators in the quantum mechanics of unitarity fermions. Now, this operator has a dimension that is different from the dimension of the two psi that makes it. The x minus y, the presence of this x minus y factor means that the dimension of the operator is 2 times the dimension of psi minus 1. Minus 1 can be thought of as the anomalous dimension of this operator. So the dimension of this operator is 2, instead of 3 as in free field theory. So the presence of the non-trivial boundary conditions, or the so-called unitarity interaction between the fermions, reduces the dimension of the charge 2 operator, and gives an anomalous dimension which is equal to minus 1. Now one can ask, how about charge 3, charge 4, etc. operators? And here the things become very non-trivial. In the charge 3 sector, in practice now we know the dimension of the operator exactly, based on a work done by Efimov in atomic physics around 1970. So he was asking the question, what is the short distance behavior of the wave function of 3 particles, 2 of which is spin up and 1 has spin down, when all the distances between the particles shrink to 0. Now this is a non-trivial problem, even when we know that if you take 1 spin up and 1 spin down particle, shrink them together, the wave function increases to 1 over r. We take another pairs going to 1 over r. But when you take all 3 particles and shrink together, Efimov showed that this wave function behaves like the overall size, which is called here capital R, to some very non-trivial number. I will show you the formula from which one gets this number in the next transparency. So the charge 3 operator can be defined by a certain procedure. We take 3 of these annihilation operators, string them together, but you have to compensate for the divergence of the wave function by this non-trivial factor r, and the dimension of this operator turned out to be 4.27. Compared to free field theory, the dimension of the lowest charge 3 operator is 5.5. So let me show you where this number comes from. The dimension of the charge 3 operator is can be read out from a solution of a certain trigonometric equation. So for in the L equal to 1, L here is the orbital angular momentum. The spin is 2 spin up and 1 spin down particle. Angular momentum L equal to 0. You have to solve these equations, find on the solution, and then put in the formula delta equal 5 half plus s, and you get this number 4.666. And the next digit is actually not 6, so 7.627, etc. And in the asymptotics region of large dimension is 2n plus 7 over 5. In the L equal 1 sector, the equation is this one, and then you get actually the lowest charge 3 operator is in the L equal 1 sector, and its dimension is 4.27. And then you have the whole series of dimensions. So in the charge 3 sector, we see here a very non-trivial behavior of a conformal field theory. We know all the dimensions with all infinite number of digits if you want to generate them, and everything, almost everything is known. But it's not the same in the charge 4 sector. The dimension of an operator with particle number larger than 3 is not known. At least we don't know how to obtain them analytically. The charge 4 dimension of charge 4 operator is known, I think, only to much less precision than we would like, 5.0 from 5.0 to 5.1, roughly speaking. Yusuke Nishida and I showed that the problem of finding the dimension of this operator is equivalent to a certain quantum mechanical problem of finding the ground state energy of, say, 4 particles in a harmonic potential. Now, one can use conformal symmetry. We can use the simple rule, conformal symmetry, to compute 2-point functions. So for example, if this O is a charge 3 operator, we know how to solve quantum mechanics in the 3-particle sector following Efimov. And we can compute the 2-point function and obtain the result, which is consistent with the conformal symmetry. In momentum space, that correlation function would be equal p squared minus omega to this power, delta minus 5 half. P squared minus omega, this structure is Galilean invariant, dictated by Galilean invariance, and this power is dictated by the dimension of the operator. Yes?
You have 1 particle number or 2 particle numbers?
I have only one. I have the spin, the SU2, and I have U1.
So when you say 3-particle sector, you have representation?
This spin one, this charge 3 operator that I talked about here is in the total spin 1/2 sector. So total spin 3/2 sector is trivial because all particles are fermions and they don't have S-wave scattering. Yeah. So it's a charge 3 and spin, total spin 1/2 sector. Yes.
Since you're already interrupted, why is it okay to ignore the possibility of a spin flip? That's not cosmic energy.
A spin flip, so roughly speaking, the following, the spin flip in the case of the fermions, of neutrons, is described by an operator which is irrelevant for in the low energy regimes. So when we have 2 fermions, like neutrons, that are far away from each other, the spin-orbit coupling is less important than just the point light scattering. You can see that in the case, for example, in deuteron, for example. The main interaction that gives rise to the bound states of a proton and neutron is the S wave. The D wave channel contribute a little bit, but not too much. Okay, so the non-relativistic conformal symmetry in the real world is realized by neutrons. Two neutrons, when they are at low energies, they interact with a large cross sections. The scattering length is minus 19 Fermi, much larger than, for example, the effective range of the interaction, which is the next term in the expansion of the scattering amplitude at low wave number. R0 is 2.8 Fermi, much less than 19 Fermi. So in the certain range of energy, namely between h bar divided by m a square and h bar divided by m R0 square, we would, roughly speaking, have a theory with no scale. Because in this energy scale, A is practically infinite, and R0 is practically 0. It's a situation of so-called unitarity point-like interaction. And we will see that the consequence of such a interaction is a power law behavior in the scattering processes with final state neutrons. Hans Mahammer and I wrote a paper in 2021, and we call such kind of power law behavior unnuclear physics. And when I sent that paper to David Kaplan, he said that it's very dangerous title. It's very close to unclear physics, supposed to be a term used by Gell-Mann to call nuclear physics. I actually never found where it is written, but I was told by Al Mueller that Gell-Mann called nuclear physics unclear physics. Hopefully, this unnuclear physics is more clear than the nuclear, than the unclear physics of Gell-Mann. It's a sector of nuclear physics where we can make a non-trivial prediction. And this is also a play on George I's articles called Unparticle Physics, in which he speculates about the existence of a sector beyond the standard model described by a non-trivial conformal field theory. So the unnuclear physics involve the following processes. We have two particles, say A1 and A2. They collide and then give rise to a particle B, and then some number of neutrons. So let's assume that this number is 3, as in this figure. In the kinematic regimes where the particle B carries most of the available energy of this reaction, the 3 neutrons have to move almost parallelly in the same directions with the same velocity. So they would move. And because the scattering length between the neutrons are very large, the interaction between the neutrons cannot be ignored until they are far away, until the distance between them is larger than about 19 Fermi. That can happen much later than the decoupling of this particle B from the reaction. And so in this kinematic regime, we can expect that the probability of the reaction can be factorized into 2 terms. The first term is the production of the particle B and an object that I call U, and we call that object unparticle U. I'm sorry, unnucleus U. And then this unnucleus U propagate, and then at some point fragment into 3 neutrons. That happens when the energy scale of the primary reactions is larger than the energy of the decay if the U to 3n. That happens when the kinetic energy between the 3 ends, the energy of the neutrons in the frame moving together with the neutrons, in the center of mass frame of these neutrons is small. So let's put in some formulas. If we think about the factorization formula, then the main factor is the decay of this unnucleus U into 3 neutrons. And the decay rate of U is proportional to the imaginary part of the propagator of this U. Now, if we identify U with an operator in the non-relativistic conformal field theory, the imaginary part is proportional to the power of how far off shell this particle is. And a little bit of kinematics show us that the off-shellness of this U is proportional to the distance of the energy of this particle B from the endpoint. The closer B is to the endpoint of its spectrum, the closer the system of 3 neutrons is on shell. So when E is equal to E0, all the neutrons are moving in the same direction with the same energy, and this is now the particle used is on-shell objects. Now, we know that the behavior of the Green's function is dictated by the dimensions, so d sigma over dE should be equal to E minus E, E naught minus E, and a little bit of kinematics tell us that the power is delta to the minus 5/2. 5 here is basically the dimensionality of space and time. So space, we have 3 spatial direction. 1 time, but in non-relativistic theory, time is counted as 2 space. E is equal p squared. So that's the origin of this 5.
How do we know they come out in the spin half, not in the spin 3 half?
They can come out in any spins and any angular momentum. We just need to choose the sector with the lowest dimension.
Like when you're close to the endpoint.
When I close to the endpoint, I have contribution to the cross-section from different operators. And the operator with the lowest dimension, we expect it to dominate.
No, that depends on n. I think the total spin.
No, this delta depends on n, right? This delta.
So the factorized part, the part that you factorize.
The part that we have factorized.
Yeah, it depends on the spin.
It depends on spin. We just assume there's nothing that makes it different sector very different from each other.
So
yeah.
That this part doesn't depend on spin very much.
It can depend, but it can be 1 and 2 or some factor of order 1. That at the end will not be important when we go to very low energies. So let's consider some nuclear reactions. We know that the sigma over dE is proportional to E naught minus E to the alpha. If the number of emitted neutrons is equal to 2, for example, in the first reaction here, it's randomly chosen among different kind of reaction that can produce 2 neutrons. Then delta, we know that the delta is equal to 2, and this alpha is equal to minus 0.5. Actually, this is known from the 1950s. There is 2 papers, one by Watson, the other by Migdal, where they consider basically the problem of the effect of final state interaction between, say, 2 neutrons, and they see that the cross section should grow near the endpoint, and then very close to the endpoint where we can no longer set the scattering length to infinity, it would drop to 0. So that the power during this growth is minus 0.5. Another reactions, say this one we will consider a bit later, absorption of pi minus pi triton. The number of neutron emitted is 3, the dimension is 4.27, and this alpha is 1.77. And if we have 4 neutrons, the prediction for alpha is about 2.5.
small and great matter, the level of the is synonymous of having a change of the operator with a minimal twist and not dimension. Does it make sense?
I think in non-relativistic physics, there's no notion of twist. It's all particles in the rest frame of the neutrons, all the particle basically is at rest. And so it's the dimension. There's no, it's not unlike in the light cone. Mm-hmm.
This to make sense, do you need more than one neutron in the final?
Yeah, yeah. In order for the spectrum of these extra particles to be continuous, you need at least 2 neutrons. Otherwise, the kinematics just fix the energy of both particles.
So can we review it like a dynamic of this, because this refime of bound state, whatever U, what you call U,
Uh-huh.
it's kind of a virtual level, right, essentially, because it's sitting on the other side, and but then it's like, no, I wonder, then it's, no, you see, it's, I am trying to present it as a dynamics of this virtual level, which are sitting on below threshold, right?
It's actually not the correct.
I
think.
wonder, yeah, it's a question, because you know that 19 Fermi
is large.
due to this, right?
19 Fermi just say that if you change the interaction between neutron a little bit, 2 neutrons will become bound.
Yeah.
But even if you change, even then, the 3 neutron state will not have a resonance, will not be resonant.
No, right, but you can say that it is interaction of different resonances because there are different pairs there.
You can say that, but I think the best way, at least the way that gives us some prediction, is actually to think about that as an operator in non-relativistic conformal field theory. It's not very physical way. It's an operator in non-relativistic conformal field theory, but I don't think it's related to any resonance.
Yeah, but it's not a resonance because it's a virtual state.
It's not
a
even
resonance, of course.
No, it's not.
But it is kind of dynamics of, instead of particle, you have something in the complex plane right now, and in this way it is still reflected in this dynamics.
Yeah, but this object in the complex plane is very far from zero. It isn't close to the real axis.
Okay.
Yeah, it's not something that's.
Thank you.
Yeah. Okay, so now I have to somehow go a little bit further. Somehow this still doesn't work. Really, yeah, non-relativistic. Near the end point, yeah. Yeah. I'm not sure what I do wrong, but okay. Thank you. Yeah, somehow there's a trick that I never learned. Okay, so a comparison with experiments. We look at the literature, and we found papers from the 1980s when people did the experiment with pi minus absorption. They create basically an atoms, the pi minus bound electromagnetically to the triton, and then observe the decay. Most of the time, decays into 3 neutrons, but there are some events where the photon is produced. I was told that such an experiment now, the type of experiment in the 1980s would be very difficult to do now because the tritium is radioactive, and the safety procedure now is much more stringent. That Bill Zeit, who participated in this experiment, told me. And also, I heard that tritium is now much more expensive than when it was done. On the other hand, when we look at the results, we couldn't find the data which is precise enough near the endpoint to compare with our prediction. So what we did was to turn to theoretical nuclear physics model calculation, in which they took argon potential with 40 parameters to model the tritons, with some vertices. There's also three-body interaction and some vertices of pion absorption, pion-nucleon interaction. And then they have a table which we got from the authors and where we make this plot. These black dot, round dots are this quasi-experimental result, basically result of theoretical nuclear physics calculation, and it fits. Here's the simplest fit is this line. You can none of the other. This one we try to improve it by including the next operator. It doesn't improve the fit very much. The line goes through the first few points. This theory is supposed to break down at large energy by the scale 5 MeV, which is h bar divided by mR0 square. Here we see that it's diverted. It diverts from theory at around 2.5. You start to see a deviation, and the next point would deviate even more. And then it should deviate at low energy around 0.1. We don't have any point here. So this is perhaps the closest. It's much closer match to experiment than we expected.
What are
The squares are the result of the theoretical calculation where the final state interaction between the neutrons are neglected. So in this case, we can think about the neutrons as free particles and take the exponent, the dimension from free field theory. And free field theory predicts this curve, which also matches with the. I actually don't know why this author plays with ignoring the final state interactions, but they did, and then we see that it's also the line also fit with our prediction. But now with non-interacting field theory, the exponents from non-interacting field theory rather than interacting field theory.
So what does it check? It checks F-loss computation. I mean, if it's the same potential, then somehow it's not going to work.
Yeah. On the other hand, it's still yeah, there is a reason why this is surprising, but later I tell you. But you can say that what we're finding here is the power of universality of low energy effective field theory. That's a very complicated theory of nuclear physics with a lot of parameters in the potential, tuned to produce hundreds of masses of the nuclei with a lot of excited state. At the end, all of that produce a result that can be predicted from a film of calculation in 1970, yeah, for three bodies. And it's a non-trivial prediction because the exponent here is not a trivial number, like 2 or 3 or 1.5. Okay, so one can think about this non-relativistic conformal field theory as a transient fixed point that we accidentally, the nature tuned to us. The microscopic theory, of course, is QCD, and then it flows. And if we look at this neutron sector, it flows very close to the point of unitarity for neutrons, almost fine-tuned the physics here, but we don't go there. We don't go there exactly. At the end we go to the state where the energy scale is much less than 0.1 MeV. The fermion, the neutron behaves like free particles. So we can think about these unitarity neutrons as a non-relativistic conformal field theory that is very close to one that accidentally nature passed through in its renormalization group flows. The unitarity neutron point has as a conformal field theory, it has deformation. It has a relevant deformation parameterized by 1 over A and an number of irrelevant deformation parameterized by the other parameters like the scattering length, etc. Okay, so dimensional counting is the following. We have non-relativistic conformal field theory Lagrangian L, and then plus deformations. All the operators with dimension less than 5 are relevant, and dimension larger than 5 would be irrelevant. So here we have one relevant deformation that can be identified with the operator O2 Decker O2, where O2 is that operator I show you with dimension 2. And you multiply them together, actually the dimension remains the sum of the two, it's 4. And the leading Galilean invariant irrelevant deformation is actually this one. It's dimension 6. All the other operator has dimension larger than 6. One can list them all and show. And this operator matches with the parameters of the low energy scattering, the scattering length, and inverse scattering length, and the effective range. Now one can actually compute the contribution to the, say, three-body, the propagator of the operator O3 using conformal perturbation theory, and that is something that I've been doing for last year or so with maybe slightly less with Subham Chowdhury and Ruchira Mishra. The idea is to treat this inverse scattering length as a small parameter in deviation from conformal field theory, and use and expand in the path integral to leading order in 1/a, and bring this down. The correction to the 2-point function now is the 4-point function, but we can insert complete set of state. We know how to solve quantum mechanics with 3 or 1 particles. And from that, we compute the first correction in 1/a in this power law behavior, and the coefficient C is something of order 1. It's slightly larger than what we expected, 2.6.
So you got stronger behavior, 1/2 of omega.
Yeah, at smaller energy, it's become smaller, it become larger and larger. The effect of the scattering length is more enhanced at low energies.
But how do you know that there is no subleading correction even stronger?
In omega? No, this will be. The whole series will be series over a square root of omega. So this correction is small only when omega is much larger than 1/a squared, which is this 0.1 MeV scale.
So for small omega, you will have to restart the whole theory.
Yeah. And we don't know yet how to do that efficiently. But in principle, this is a problem that has to be solved.
But it's exactly what I was referring to asking the question, because once again, if the theory were relativistic, it's exactly these theories which synonymous of assignment certain number of infinite set of the operators. And the relativistic theory, those are operators in the leading list.
I don't, yeah. I would like to talk to you about that. Yeah, it's an interesting problem that we would like to solve. Yeah, when we try to compute effective range correction, we find some integral, and then this integral turn out to reduce to a gamma function, which gives us 0 in the physical dimension, d equal to 3, but not in fractional spatial dimension, and we don't completely understand why it is so.
But it means that it is next order
It will be next order in R0, but the leading order in R0 is 0. Yeah, we do not understand that. Okay, so the open questions: can we resum all this 1/a correction, determining the correlation along the RG flow instead of using conformal perturbation theory? Can we do the full things? Can we compute correlation function for charge 4 operators and higher, etc.? So let me skip this. So to conclude, QCD has had a large cultural impact on condensed matter physics. Here I'm talking about somewhat a different problem, non-relativistic conformal field theory with Schrodinger symmetry, and we've shown that thinking about that as a non-relativistic field theory, applying methods of conformal field theory, conformal perturbation theory, could give us interesting results. Thank you very much.
A couple of questions.
So, from the point of view of two-body interaction, this model only has two-body interactions, right?
Which
The original heavy like ions, they are modeled by two-body interaction.
the unitarity fermion.
Yeah.
Yeah, unitarity fermion has only boundary condition when two particles.
Okay.
Yeah.
Now, in quantum mechanics, there is a whole family of boundary conditions which have infinite correlation length, infinite scattering length. These are the 1/r² potentials, which are above the unitarity bound. So how do they fix this coefficient?
1/r² is not, 1/r² is conformally invariant,
Yes.
but they don't appear in neutron, physics of neutron. It's too long range.
Okay.
The interaction between two neutrons is only one, it's
So they add the delta
Yukawa.
function. So they effectively add the delta function with that fine-tuned coefficient to
With the
reproduce
fine-tuned-
infinite correlation length.
Yeah.
And 1/r² just doesn't appear in heavy ions. That's what
It
you're
doesn't
saying.
appear in nuclear physics. It also doesn't appear in atomic physics, because in atomic physics, the long distance is like 1/r⁶. It would be very interesting to find a way to realize this 1/r² experimentally. Then you would have a whole new set of family of theories with different continuously tuned parameter.
So for relativistic theories, scale invariance usually implies conformal invariance. For non-relativistic theory, I'm not aware of such a statement. Or is it kind of a miracle that there is full like this enlarged conformal symmetry here? Could it have been just dilatations? Or?
So there is one way that I know that, well, in simple theory, I'm not completely sure. In theories where these operator can be written as an integral over density, current density, and momentum densities, one can show that the conformal invariance, scale invariance implies conformal invariance. But I don't know how general that statement is. In all examples that I know, this is the case.
Yeah, so in this case where there is no huge scale separation, would you worry that you don't really see a clean scaling exponent, it just drifts sort of?
Yeah, I actually, after the calculations that we did, this number, if you put in there 2 divided by, the correction is larger than that graph that we plotted would suggest. So let's see. This number, the correction is numerically large, but somehow we see that fit in this. Maybe it's accidental that we see the fit working well. Yeah, but I think if we can resum all this 1/A correction, which is a well-defined problem, because we have a well-defined renormalization group flow, and then the fit would be much better.
And just it's slightly off topic, but what would you consider like a very clean example, field theoretic example of unparticle physics?
A very clean?
Yeah.
Yeah, so this one is clean.
No, not unnuclear, but
unparticle physics. Unparticle physics, I try not to think about them.
Yeah, maybe optimistically, unclear physics is clear physics.
Unclear.
One more question. Can you say anything about the virial coefficients for neutron gas?
A virial coefficient for neutron gas? No, but I don't. You want to understand the virial coefficient in the regimes where the energy of the.
In terms of the normal dimensions of your operators, for example.
I'm not sure if it's actually. It's an interesting question. Actually, I actually haven't thought about that. So there's a virial coefficient that comes from 3-body interactions. That's what
third virial coefficient will depend on 3
three-body interaction. Yeah. Yeah.
Some work by Joachim Druth and collaborators
Yeah, I think this will be interesting. Yeah, it's an interesting, probably some fractional power dependence on the temperature, but I don't know. Yeah, this is in the regime where I actually don't know if it exists in nature, because you need a very dilute neutron system. Yeah, and this dilute neutron system would decay, because neutron decays into proton and electron. So I actually don't know if such a regime can be realized. Yeah, so that's why I haven't.
It can't for cold atoms.
It can't for cold atoms. Yeah, but then yeah.
Okay, why don't we conclude there? I think.
Thank you.